Great. Our next speaker is Deepak Pathak. He is currently at FAIR and starting very soon as assistant professor at CMU. In the context of self-supervised learning, he has done many different things. He is involved in the context encoders, multimodal image-to-image translation, and very recently also the curiosity-driven learning work for RL agents. So we are very much looking forward to your talk, and the stage is yours.
Thank you, Christian. In fact, on the topic of Facebook and CMU, today is actually my last day at Facebook research, and from Monday I started CMU. So it's a perfect transition. So this is the last time I'm using two affiliations here. Okay, so since the workshop is about self-supervision and what are the next steps in self-supervision, so I thought I start with the question is, why do we need self-supervision at the first place? And it's funny to ask this question since most of my PhD was on self-supervision. So I'm asking this question at the end of the PhD. But this question is a very practical one. From the practical perspective, we already know that deep networks works really well on several of the tasks. In fact, the key reason that they are so popular is the fact that if you train them on one task, let's say finding or classifying images, they transfer very well to a number of tasks. And this behavior is not just seen in vision, it is seen in speech, language, in every domain, where if you train these networks for one task really, really well with large amount of data, you can still transfer very well to the next task. So that's why the question, why do we need self-supervision? Well, if it's only one domain we have to train on, we can always get the labels for, like ImageNet has been working really well for everyone. And in fact, currently the highest numbers in every task that we care about in vision are from a model which is pre-trained from ImageNet. So why do we need this kind of self-supervision training? And one of the reasons I would say is the fundamental argument for self-supervision is that of generalization. So for instance, we can take these results from ImageNet. This model performs really well on these images and achieves very high accuracy. But when we test the same model and try this on data from the real world, let's say a video from a YouTube over here, the model completely fails to generalize. It finds things like snake, cobra snake. It finds things like gray fish, flatworm, right? So what is going on? Like the model that performed really well on ImageNet drops to a very low accuracy on these different examples from the real world videos. And the reason is the fact that these videos, the distribution of the data is different from what it was seen in the images. Like these examples are not, the object is not at the center of image, it's moving, the lighting conditions can vary, etc., etc. But fundamentally, the key challenge here is the fact, is the assumption which we in machine learning or vision have been hiding under the rug for several years. And like if you open any machine learning book, on the first page, you will find this assumption that let's assume that our distribution, our training and test are the same. But in real world, this assumption gets falsified all the time. And our system that work very well at training time completely fails to generalize. So we don't know how to adapt these systems continually to changing domains. We have already perfected these things on data sets. And as in the previous talk, Alesha rightly mentioned that maybe it's time to move beyond data sets. And but the question is, we don't know how to adapt this. And in order to approach these, in order to build these ideas, we need a setup where we can study things, where things are continually adapting. And in order to adapt continually, self-supervision has been posed as a solution over and over several times. But if we look at the literature in the past several years, what we have done with self-supervision is we have applied self-supervision to data sets. Like lots of works in the last 5-10 years, even in 90s, going in the audio visual domain. All of these setups are fundamentally applying the idea of self-supervision in these data sets. Even in the case of video, because video is continual, stream is coming continuously. Why are we still applying all these methods on the level of data sets when we know the fundamental problem over here is the data set. We are not able to adapt beyond what we are training on. So for instance, the result I showed for ImageNet of generalization, I'm pretty sure that if we train those models with self-supervised learning, the generalization to videos will still be equally hard, right? So self-supervision is, we know its answer to something. It's certainly the right thing to do because humans do it all the time. And we have ample evidence from psychology and infant studies, child studies, that this is how things should be. But where are we going wrong in being able to develop these approaches? So the question I asked today is, if self-supervision is the answer, what is the question that we should be asking? Like, what is the setup we should be studying self-supervision on? And fortunately, Alicia has already given a very good primer for this by mentioning a few points. And I would reiterate them and add some of my points over here, that I think there are three key questions that self-supervision rightly answers. And they align with our very much practical goal, as well as the scientific goal of understanding how to build intelligent systems. The first question is, self-supervision could be a good solution to study the goal of how do you continually adapt and generalize. The second question is, self-supervision can also help us address scenarios. So to study self-supervision, second question we should ask is, where do we study it? Do we study it in the context of data sets, or do we study in the context of continual learning? For instance, the example Alicia was mentioning for a smooth change over the scenarios. So you can apply SSL in the setups of data set, or you can try to create these benchmarks for continual learning where you have take examples from one data set and permute them. But at the end of the day, they will either be too easy or too hard. And you have to naturally ensure this smoothness. And the third question, which self-supervision can also be an answer for, if it can also allows the agent to be able to choose its own data. And when we are applying these techniques in vision, especially in case of passive vision, we compromise all these points, which are the strengths or the reasons one should use self-supervision for. Like at the end of the day, if you are going to apply self-supervision to passive data sets, you might as well have labels or do transfer learning from ImageNet, and that will perform well or equally well in all those setups. And these are the fundamental reasons one should argue for self-supervision. But the way we have been doing this, and I am partly guilty of this as well, and so is Alicia as well, because we have already had multiple papers in these applying self-supervised learning on ImageNet or Pascal, but we have to start somewhere. But now thinking what's next in self-supervised learning, we have to really go towards the setup where these things are answered naturally. Because no matter what you do, it's very hard to craft these setups which are continual, which are changing smoothly, select the agent is allowed to select data of its own. However, meanwhile, in the world of robotics, what are the key challenges? In fact, it turns out these are the bread and butter of robots. These are the exact challenges which robots face every day. And that's why the progress in robotics is much far behind where it is in the case of vision. Because we cannot really build data sets. The data is continual, it's not IID. It changes smoothly, fortunately, because it's mounted on a robot size. It has camera on itself. It is active, embodied, robot can choose its own data. So you have all the nice properties in this domain where you can actually study and build these self-supervised algorithms, which can hopefully generalize to something new. To further enhance this argument, unlike passive domain where you can train on some tasks like vision or NLP in language modeling, it's very unclear in the case of embodied agent, which task do you even train on? For instance, over here, a normal person does so many tasks every day. And if you go to the route of supervising these tasks as we go in vision, you will spend billions and billions of dollars in a matter of months in trying to label these examples. And so once again, self-supervision is the only way to go in these domains. Second, there is also it's very hard to standardize these settings. Like for instance, there is a phase of curation of data in vision where we curate data and we learn on that data, and then we apply self-supervision or supervision on that data. And in today's talk, earlier in the workshop, Andrew Zisserman talked about uncurated phase. And that phase is already there in robotics. For instance, there are so many robots which are all different. No two robots are the same. there will be some change even between the same robot from the same company. And you have to fundamentally address this problem at the level of data set itself. And because of these reasons, generalization is much hard, and the gap between what one could do and what we are able to do right now is very huge. For instance, we have systems that can perfect and do really, really well on one task. But unlike vision or language, where transfer learning works really well, the transfer in robotics is just not there. These approaches completely fail to generalize, and even though we can do parlor tricks as on the left, the mere task of putting a box on the table completely falls apart. And this is why one of the reasons I would argue that self-supervision is rightly and naturally belongs to the domain where an embodied agent goes and collects data on its own. And in fact, this view is not a modern view. It's not in hindsight. And in fact, this is a paper from 1988 by Bartlett Mell. And what he proposes over here is that a robot should learn about its own structure and its own actions by acting in the world. So what he proposes is an architecture of learning about motors and joint actions, where the robot goes around and acts in the world, moves its arm, and from the perception system, it can see where its arm is. And the alignment between perception and action acts as a feedback to learn control. Now, this is basically self-supervised learning. And if you see, it's like from 1988. And the earliest reference in the passive domain for self-supervision we find is from 1996 or something, which is the audio-visual work also from Europe, I think, around 96. So this is how it began in robotics. But for the last several years, the picture has changed a lot. And I'll give you some examples of that. How do we currently do things in robotics? And from there, how can we go to using self-supervision in the context of embodied agent? So for instance, let's consider the task of this robot over here. Now this robot has a task of tying this rope from this position to this next position. And in this case, the goal of this robot is to output some actions. So how do we currently approach this problem in the context of embodied agents? So currently there are two major paradigms of solving this task. One of the first paradigm, which is very close to the way we solve things in vision, is of supervised learning or imitation learning, where a person comes and controls the robot manually to give demonstrations of each of the action and the state pairs. Now, this is very tedious for the expert and very hard to generalize because it is specific to the task it is trained on. And it has all the problems that we face in terms of passive learning on fixed data set and fixed distribution. It does not generalize. So there is this other regime of task of reinforcement learning, which has been proposed as a very general solution, where the idea is as follows, that you start with some information at the top, let's say current image, and then you train a policy, which goes to output some actions, and the next state, and then eventually it is a goal. And the idea in reinforcement learning is that when you reach a goal, you get a candy or some jackpot of +1. And your task here is to optimize and maximize this reward over time. But the catch is, this policy in the beginning starts being random. And if you start randomly from this position, how likely is it the case that the robot will just end up tying the knot? Well, it's extremely unlikely. From one of my estimates, roughly in this setup, I think it should take these many interactions to tie the knot once, which is huge and very, very inefficient. So the picture in practice in robotics is much less glorious. The way it works is as follows. You might have seen its results where an agent can learn to play the games by only looking at the pixels of the screen and no other information. But the catch is these algorithms use score of the game as a reward, which provides a dense supervision at almost every time step. Even in tasks like navigation, where the goal is to reach some end location, most approaches today shape the reward function by providing these apples over here. But real world does not give you apples. In real world, the reward could be delayed by days, months, or year, such that it's hard to propagate back to where you are. So how does this child over here know? How should she act to become pilot 20 years later? Does she backprop gradients all the way like we do in RL agents? And perhaps not. In fact, similar to the Murphy's argument before, developmental psychologists have argued for several decades that these babies are not driven by this end goal of trying to achieve something at the very end, but they are driven by their self-supervised intrinsic motivation, where they just do things for the sake of fun, And by doing that, they learn skills which can then be used to solve future tasks. So the question is, how do we even define this curiosity signal? And in fact, in today's talk, I'll show you some of the examples of how do we go about solving these approaches, which will in some ways rhyme a lot with how we do things in vision. But we just extend those approaches towards the action domain to get similar insights. And as a benefit, we get our agents to function very well in the new environments. So there has been a lot of work in the past in the domain of exploration and intrinsic motivation, but most of these approaches previously relied on in the context of external goal. So there was still a goal at the very end, and the question was, how do you explore for that goal? But now in our line of work, what we have been doing is how do we build algorithms that can explore completely on their own without having this target of finding a goal. So the idea is really simple, and it's fully supervised, or sorry, fully self-supervised. The way it works is that we start by building a model. A model is in a way basically suggests if I do this, what will happen next. So I have an agent which has some actions, and I take the agent and it applies the action, and it predicts what will happen next. So it's basically future prediction in a way. Now we employ prediction. So what agent does, it just goes around and makes predictions about what will happen next. But now, since the world is embodied, the agent can continually go around and predict consequences, and it can also attempt those actions and then observe how much is the error in what it is doing. And whenever the error is high, the agent becomes more curious. And when it becomes more curious, it goes back and again again explores that scenario further. So whatever agent gets curious about, it goes and explores further. As it explores it more, it gets more data. And as it gets more data, model improves. As the model improves, error goes down. Agent becomes less curious. When it's less curious, then it has to find something else to be curious about. So in a way, if you can see, with this action in loop, with just one dimension extra, which is on top of vision, you have just action extra. With this one action extra in the loop, agent is able to continually learn on its own, continually get its own data, continually improve itself, and continually find next challenge for itself. And I'll show you this result with an example of a very toy scenario of Mario game over here, where if we hide the reward function, so the agent is completely self-supervised, so there's no idea what to do in the beginning. It is just jumping around. It is building a model of how the world works, and then it tries to be curious for some time. So in the beginning, it knows nothing. By mistake, it may kill an agent, but it's not doing much, which is interesting over here. And after some sort of training with this curiosity learning, surprisingly, what ends up happening is that the agent learns to discover data for itself and continually improve itself to go on and on and on until its curiosity saturates. So it ends up finding all these 10 levels and makes progress through. So it goes to like 10 or 11 levels, much farther than I could go in my own childhood several years back. And this works surprisingly well. And in fact, we have scaled up this idea to a large variety of environments since then. And what we found that the same idea actually is able to discover interesting behaviors, not just across one game, but across multiple games in simulation, like Atari over here, these robots on the top, which walk in simulation, etc., etc. So we were curious, okay, maybe this seems like the right way to go about things. And now, since we have a bottom framework, now can we build upon it to actually build practical systems in the real world? So we are really curious about applying these ideas in the real robot scenarios. And when we attempt these ideas in the real world, this is what happens. So here is a curious robot. And again, there is no task. So it is just doing something stupid. So it's basically completely failed. So this is a negative result. So nothing worked out over here. And one of the reasons nothing worked out is because we developed these ideas in simulation and they worked well, and you can optimize prediction error, but they are still very inefficient. And for instance, in vision or in simulation, you don't have to worry about efficiency ever, because at training time, you can take as many samples as you want. You can take, in a matter of a few days, you can take a million samples or million examples. But in the real robot, if you go about taking million samples, I would have spent all my PhD in just to get one experiment right? So what is the key reason? Why is it so inefficient? Like if the agent is completely self-supervised, shouldn't it be able to discover its own data very fast? Well, one of the reasons it is very inefficient is as follows. I'll just go quickly over the reasoning. So earlier in the description, I described that agent has a policy which it uses to explore, and then it builds a model of how the world works. Given the current image and the action, it predicts the next image. Now it computes this next prediction to compute an error. And this error we defined as curiosity earlier, correct? Now, if you notice this error actually depends on the next state that is obtained by acting in the environment. So it depends on this xt plus 1. And since the environment is black box, you cannot really optimize this function directly. So what you end up relying on is reinforced like optimization, which is hit and trial, and you try multiple things until you can optimize this objective over here. But what we wonder is the fact that since the agent is building its own model, it's being curious in its own mind, why does it have to use reinforcement learning, which was fundamentally developed for finding rewards which are extrinsic to the agent? So what we did was we make one change to the agent over here. We take the model, and instead of building one model over here, we build a bunch of the models. And they are trained the same way to minimize the respective prediction error. But we make one change, that instead of using prediction error as the notion of curiosity, we use the disagreement of these models as the notion of curiosity. So for instance, we build multiple models, we compute their variance in the output, and then we use that to train the agent's exploration policy. Now, first of all, why is it going to work? Well, if there is a scenario where agent cannot predict what will happen next, its variance will still be high because it does not know that example yet. So in the unbiased case, variance will exactly correspond to the error or the uncertainty of the agent in the environment. But the nicer property of this metric is that this variance actually does not depend on the next state. You can just compute variance by only looking at your own models of the world. And so this is completely differentiable and no dependency on the environment. So you can just train it in a very efficient manner in an end-to-end learning. And with this in the loop, you can get around the inefficient objective of reinforcement and just train it very fast in the real world. So one example over here, when we apply these ideas to the real robots, what we notice over here is that this is, before I show the result, let me show you a result of what will happen if I train the robot with random exploration. So it's basically randomly exploring, which is the most common way people used to use robots for robot learning experiments. But if I let these robots explore randomly, it does not even touch the object for a very long time. But despite this, you would have seen lots of papers coming out from different labs where they can do robot learning of pick and place tasks, for example. And the reason they are able to do very well is the fact that they put lots of objects at one location and they have lots of robots. So if robot just goes randomly over there, if there are too many objects, it can still pick up any one of them. So we made the problem harder by having only few objects in here. So since the problem is much harder now because of few objects, now our idea can we use curiosity-driven exploration, which is a more efficient version of using disagreement to solve this problem. And what we found that the same agent in just 5 to 6 hours of training goes from randomly exploring to finding objects, picking them up and putting them in different places. And it's learning a direct mapping from exploration to these actions over here. But in the end, again, from a more practical head point of view, the exploration is just not useful if I cannot control it manually to solve some external task. So how do we go from exploration to achieving goals? And for this, what we use at the very end is we just take the model the agent is building. Because since if the agent is building a model of how the world works, if I have that model, I can just use that model to plan in my mind, how do I go from here to here by trying out different alternatives. And this is one of the ideas which we have been building upon for last several years. And in the latest work in this ICML, we are able to extend these ideas to multi-step prediction. So the key notion over here is that we incorporate the task of planning, that we incorporate planning intrinsically into the exploration phase. So in the same picture as before, you have a policy over here, which is learning to explore. Then what do you do in imagination? Instead of being curious about one step, you become curious about multiple steps in your imagination, and you and you predict what will happen if I do this, and then what will happen, and then what will happen, and then what will happen. And at each of this step, you compute your disagreement to compute the curiosity, and then you backprop all the way to optimize this model end to end. And what we found that using this approach, even without using any sample from the environment which contains a reward to train the model, we are still able to perform as well as an oracle which has access to reward from the environment. So the orange curve over here is the oracle, and green is the our method. And in some cases, if you notice, it does even better than the oracle. And the reason is because it is not training for one task. It is training in a more generic sense of curiosity, and it's still able to adapt fast. And that's why it is able to do better in some of the tasks. And sometimes it does exploit the simulation. For instance, over here, it is able to, since it is not training for the task, it is training in a more general curiosity way. So it is able to discover a different solution to achieve the task than a normal agent will do. So what we do is we just add 15 or 20 more episodes. And when we do that, the performance, first of all, the performance matches in all the scenarios where it was lower than the oracle. But it also fixes many of the behaviors by just using few examples at the very end. So now if you see, after only 15 to 20 episodes in the setup, it is able to adapt to the nicer scenarios, to get nicer behaviors. We have also applied similar ideas of planning as a tool to go from exploration to achieving real tasks in the real robot earlier as well. And here is one example of that. So for instance, the task I showed before of tying knots, which is hard to do from an RL perspective or from an imitation learning perspective, what we do is we allow the robot to explore and collect data, and then we use this data to build models, and then use planning at test time to ask the robot to solve this task. So for instance, for tying knot, a human comes and shows only one example at test time. So the agent had been continually learning, and then at test time, someone comes and showed one example, and the robot can use its own knowledge so far to solve the task. Yeah, so it is able to tie the knot, even though it is never trained on this task at test time. So it was continually learning completely on its own. I think I have 3-4 more minutes, so I'll just quickly, right, Christian?
Yes.
Okay, sure. Okay, so I'll move forward. So far, I covered the aspect of generalization across goals. So I talked about the scenario of where when we train robots like a baby, because I think this slide is something wrong over here. So far I talked about generalization of robots across goals. And we showed that how curiosity and self-supervision can act as a measure, or can act as a way to pre-train these robots without making them specific to a task, such that they can generalize to new scenarios or new tasks completely at test time without any further training. Now, as in the case of babies, our robots do start from scratch where the software does start from scratch, which is fine in the case of a passive domain. Like if you are an agent solving ImageNet tasks or videos from YouTube, the starting of software from scratch is fine, but our robots are embodied. And even though their software starts from scratch, their hardware is still this complex body of the robot, which has this 20 motors or so, and it's really complex. So can we also go about starting the hardware from scratch? Because if starting software from scratch already gave us generalization in terms of goals, can starting from hardware give us generalization across different robot types? So what we also studied is that if can we take motivation from a bigger picture in the evolutionary sense, and start these robots from really simple limbs, as in the case of evolution. And if you go much back into the timeline, and why not just humans, not to babies, but all the way back. But if you go all the way back, what is the fundamental ideas in nature which lead to this complex hardware that we have today for across different biological agents? And one of such ideas, which can be so-called Big Bang of evolution, is this idea of single cell to multi-cell. And this was the phase, first time in nature, when things went from always competing to combining. So things went from competition to collaboration. And this idea, and when they combine, they share their objective and they behave like a single agent. So this idea of compositionality has been exploited and very useful in language as well, and somewhat in vision as well. But even in the vision task, most of the cases where we have found it to be useful is when we have language pairing with the data. So we try to leverage this idea, but in the context of hardware. So what we do over here, instead, in order to generalize across different robots, instead of training a policy for the full robot, we train policy for each motor of the robot. And the idea is we allow the robot to self-discover its own morphology that can work very well for the task. So we are exploiting compositionality not only at the level of software, but also at the level of hardware. And over training time, we want the robot to build and do interesting things. So this was the work in the last NeurIPS. And here are some, I'll just show a very short video to show what kind of results do we get over here. So we had this toy environment to begin with, where we had multiple robots which can just roll around. And these robots are really, really stupid. They're like cells. They have just a limb and a motor. They cannot do much. All they can do is they can combine with each other and apply torque. And over here, the task was to stand up. And what we found that during the course of training, these robots can discover shape which is optimal for this task, for instance, to stand up. But now the fun part was that once we trained these robots for one task, they were able to generalize for new scenarios without any further training. So for instance, we can take the same robot and we can put them with twice the number of limbs, and now they can discover this new shape, because making a tower with twice the number of limbs is much harder. So it makes this new shape over here, which is able to stand up and do interesting things. But if you have fewer number of limbs at test time, then it makes a perfect tower because it's an easier problem. And there are more results over here. We can generalize to new scenarios, new domains as well. But this was still being applied in the case of these self-assembling robots, which are very hard to find in nature. There are some examples like slime molds, but this is not very useful for practical robotics. So what about normal practical robots? And in fact, in one of the recent work, we applied these ideas in the context of practical robots to generalize across not just one or two robots, but across a diverse variety of different robots. The same question as I discovered earlier. And the key solution, the key insight we are after is that once we have trained this robot, we should be able to transfer to new scenarios at test time directly. And this is, in fact, a bit more challenging problem than what we discovered before, because now not only the agent shape is changing over time, it also needs to learn different behaviors to make different agents walk. For instance, humanoid needs to walk, hopper needs to hop. Every agent over here needs to work separately. So why is it even possible to solve this task? And in fact, again, the same idea of looking at the bigger picture of evolution, in biomechanics, what people have found that very different species like humans, cockroach, crab, and dog, they even though they might have different gaits and different body structure, what the force that they apply on the ground while walking is still shared across all these species, which was a very surprising result from these scenarios. And again, you also have examples of these precocial animals which can just walk as soon as they're born. So inspired by these ideas, we apply the same idea of sharing policy across the motors, and we get these results where we are able to find a single policy that is able to control a diverse variety of agents just by, even though it is completely shared across all the motors of all the agents. So it behaves differently across all these agents and is still able to make them walk. For instance, over here, it is able to show different gaits. Like if the same policy shared everywhere, it is able to work very well across all these scenarios. Now, the main reason why we train them at the first place, or why we allow these agents to discover their hardware, is the fact that we want to generalize to unseen scenarios. And if we keep on held out agents of the same distribution, it expects to work, and it works fine to new test time agents. But we also wanted to test on out of distribution agent. Like, does the fact that you are exploiting modularity and the agent is learning its own hardware over time, does this allow it to test on new and very different agents? So what we found over here is that with very different looking agents, it is still able to do reasonable behaviors without ever being trained on them. So for instance, over here, it discovers a new gate at test time. It's a very different agent from training. It has very heavy arms, so it tries to use its knees to move forward directly at test time. Never seen this at training time. It has multiple legs. It has never seen multiple legs, so it is able to do reasonable things over here. And you can also put objects on top. It does not excel and does not move forward very fast, but it is still able to balance itself and not completely fail. It also fails sometimes. For instance, over here, if you make the limbs really heavy, the muscle power is not enough to let the agent walk, so it just falls on itself. Over here, it has no legs, so it uses hands, but completely fails to generalize. So there are some scenarios where it fails to make progress. Finally, at this last slide, we are also attempting these attempts in the real robotic settings because you have robots and you can share the policy on the motors across all these places. So for instance, this is a result where modularity is explored at the level of hierarchy, not at motors right now. This is still ongoing work, and it is able to move forward. And similarly, in the hardware case, this is able to walk with these kind of ideas. So in summary, I first started with by describing that in the context of self-supervision, robotics domain provides a very natural setup where these ideas can be studied and we don't have to work hard to carefully architect our design and our setup. And then I showed you a couple of examples of self-supervision where these ideas could be useful. Firstly, in the sense of learning during the lifetime of the agent, we explored the idea of curiosity to generalize across goals. And then I talked about the idea of modularity, where the agent discovers its own hardware to generalize across scenarios. At some point in the future, we want to put them together so that agents can generalize across hardware as well as across goals, but we haven't yet been to those points yet. So with that, I would thank you.
Thanks a lot. That was a very interesting talk and maybe a bit of a different perspective on self-supervised learning than from pure vision team. So while we wait for people to type their questions into the QA box, I have one question on the curiosity work. As far as I understand it, this works really well when the environment is very deterministic and you can really always predict in the ideal scenario what's going to happen next. Do you have any intuitions or ideas what to do when are things in the environment that are hard to predict, where the curiosity cannot succeed?
Yes. So for instance, I think this is, at least I didn't go into the details for those questions, but we do have experiments where, for instance, the agent is walking around and there is a TV on the room. If the TV is playing something, so the way we implement curiosity is that these models are making predictions, but they don't predict in the raw image space. They predict in a feature space, which is learned continuously over time. And the way we learn this feature space is by predicting the action between the current time step and the next time step. So if there is some noise in the environment like television playing, it doesn't affect agent's own action. And in that scenario, it does avoid the television. But there is still the case when you might get stuck. For instance, slot machines. When which are almost random, you are in a casino and playing continuously, and your actions are the ones that are defining the disturbance in the environment. So it's very, or an example of agent tossing a coin in its own hand. It has no idea where the noise is coming from. So in those cases, it gets very hard to avoid these scenarios. But one result over here, which we had in case of disagreement, that gets around this issue very nicely. Because in the case of disagreement, even if the environment is stochastic, you are training a bunch of ensemble of models. So if it is stochastic, all the models will go to the mean prediction and their disagreement will go to 0. The agent will get unstuck in a normal scenario. So like in the case of television, when the agent has a remote of the television, a normal curiosity will get stuck, but the disagreement-based metric can still make progress and move forward.
I see. Thank you.
Thank you.
There's no questions from the attendees. Are there any questions from the panelists, from the speakers, perhaps? Might be, perhaps.
Otherwise, we're already 10 minutes over the time anyways, so if there's no more questions, then we thank Deepak again. There is actually a question coming in right when I try to wrap up. The question is related to non-deterministic environments. Do you think in curiosity attention is important?
Yes. Yes, I think it is important, but the question is, you still need something in the objective for the attention. So since it's completely supervised, so they completely self-supervised, so there is no such task which is at the very end that you need something to learn attention with. So for instance, in the disagreement case, the attention, the objective does allow you to move forward, but if you had attention in the feature space or the from vision to features, if that module had some attention, it would make the task easier. So I'm pretty sure that attention will help, but that does not it does not conflict with the question of the objective. You still need the objective to allow the attention to help.
Perfect. Thank you very much. Good. Then the second session concludes here. We want to thank all our speakers again. It was a very diverse view on a lot of different topics on self-supervised learning with very different ideas of how to continue. We will upload recordings and possibly also slides of the talks to the ECCV website and also our website. Thanks for attending and listening to all these talks, and we hope to see you soon again.